Welcome, and in this video course we are looking at the CyberOps Associate version 1 course. This course is going to cover the skills and knowledge needed for successfully handling the tasks and duties, responsibilities of an associate level security analyst working at a security operations center. The goal of this video series is to help prepare learners for the Cisco 200-201 certification that's focusing on understanding the Cisco Cybersecurity Operation Fundamentals course known as CBROPS. Module 21, Cryptography. So in this module, we're going to be looking at asystematic keys. We're going to be looking at the PKI subsystem. That's the public key infrastructure. We're going to be looking at integrity and authenticity, confidentiality. We're going to be looking at public key cryptography and their subsystems, as well as applications and impacts of cryptography. So what's really funny is oftentimes I get asked, well, what's the important portion of cryptography? And that's the integrity and authenticity, as well as the confidentiality portions of cryptography. Those are the key things when we're dealing with cryptography. So our first major section is integrity and authenticity. And when we look at this, we're looking at four main elements: data integrity, original authentication, data confidentiality, and data non-reputational. The fun part is with the integrity, that's guaranteed the message wasn't altered or molested in transit. Open authentication guarantees that the message is not forged and actually is from who claims it is. Confidentiality guarantees that only authorized users have read the message. And the non-repudiation guarantees that the sender cannot repudiate or refute the validity of the message. Basically, with non-repudiation, you cannot refute. Basically, you cannot say, I didn't send this. It is guaranteed, it is verified that you are the individual that sent it, or the sender is the one that sent it. They can't refute or refute that fact. Alright, so what are some of the systems that work with cryptography? Well, one is a hashing function. And a hash function takes a plain message, or plain text message, and you'll go through a hash function using a specific algorithm. That will then provide a fixed length hash value. If anything was modified in the plain text message, anything, a space, a dot, a period, anything, it changes the hash value. The hashing is based off of a one-way mathematical function or formula. The hash function will take a variable block of binary data called the message, and again produces a fixed length based off of the algorithm. The resulting hash is also called the message digest or fingerprint. With hash functions, it is computational infeasible that two different messages ever calculate to the same hash value. Every time the data is changed or altered, the hash value will also then be altered. So what's the formula? So if we're looking at a hashing function and there's an algorithm, well, what's going on? So mathematically, the equation is little h equals big H x. And this is used to explain how it operates. And x is going to be the message, big H will be the hash function algorithm, and then little h will be the hash value. So again, the hash value equals the hash function, and x will be the function of the hash. The input can be any length. The output is a fixed length. The function hx is relatively easy to compute for given x value. One way. So the function of hx is a one-way, non-reversible, and typically it is collision-free, meaning there should be very, 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 very small possible responses where little x will ever give the same little h value when you do the same hashing function algorithm. That's called a collision, and it's very, very, very unlikely that will ever occur. So the next question is, I keep saying hashing function or algorithm. Are they all the same? Are they all created equal? And the answer to that is no, that they're not. So here we have two very common types. We have an MD5 and we have a SHA. So hashing functions, again, they ensure the integrity of the message. They make sure that the messages were not molested or not modified. And there are a few different well-known hash functions. SHA has SHA-1, 2, 3, 4, 5, 128, 256, 512, and so forth. So you have the higher versions of SHA. SHA-1 typically is SHA-1. It's very similar to MD5, and it has a 160-bit hashed message. Slightly slower than MD5, but it is also now classified really weak. MD5 is 128-bit digests, one-way function, produces a 128-bit hashed value, and is considered a legacy, and is also not as secure. SHA-2, that's going to be the family, that's going to be the 256, the 512, and greater. SHA-3 is the other family, which is, again, more next-generation algorithms. Alright, so what do we do? How do we make sure that this is correct? If we have a payment, for example, pay to Alex, value is $100, and we get pay to Jeremy and it's $1,000. If we actually hash the messages, the hashing values will be different. And you can see that with the start and ending hash. Let me grab my pen. And again, this isn't the full hash value, this is just a portion of it, but they should be different. One of the first things that we would ask ourselves is, what is the hashing algorithm? First, is the same algorithm being used on both? You cannot use one algorithm on one and one algorithm on the other and compare them. That's not how it works. The same hashing algorithm has to hash both to verify that the hash values are actually different. So the next question is, why carry out the hashes? So hashing can be used to detect modifications or changes or molestation of the original message. And it can be used to guard against deliberate changes that are made by a threat actor. If something is sent and it's not modified, you're good. If it was sent and it was modified, you can at least know that. There is no unique identifying information from the sender in the hashing procedure. You don't know what type of hash it is. It's a fixed length, and that's kind of all you have. This means that anyone can compute a hash for any data as long as they have the correct hashing function. So if you want to hash a message using SHA-5 or MD5, you can. As long as you have the data and you have the algorithm, you can hash it. Therefore, hashing is vulnerable to typically man in the middle and doesn't provide security to transmit the data. The hashing portion is just about integrity and the original authentication, and if you want more than that, something else is required. Hashing algorithms only protect against changes, and they don't protect against data from changes by a threat actor. Hashing is the way that you can verify the authenticity of the data. If you think the data was modified, compare the source to what you received, and if they are identical hashes, you know they are fine. If they're different values, you know something went wrong. So what does it mean when we talk about the original authentication? So essentially, we can add authentication and integrity assurance by using an HMAC, or a hashed message authentication code. These are used in addition to a secret key as inputs to the hash function. We also have things like message authentication code, or a MAC, and these methods are also used. HMACs are used in many systems: IPsec, SSH, SSL, TLS, and more. Keep in mind, when we talk either HMAC or MAC in cryptography, that is different than a MAC in network communication. We use the same acronym for multiple things, so do keep that in mind. When we're talking cryptography or authentication, MAC is message authentication code, not media access control. Alright, so how does the HMAC fit into our hashing algorithm process? So what happens is we have a plain text message, we have a date of, or a collection of data that's X amount large, and we have a secret key. So this is where the HMAC comes into play, because the HMAC was going to be using that secret key. Remember that the HMAC is calculated using any algorithm. Only the sender and the receiver should know the secret key, and the output of the hash algorithm will be dependent on that secret key. So again, only parties who have access to the secret key can compute the digest of the HMAC function. Basically, if you try to do this, if you want to do an HMAC and you don't have the secret key, you're not getting the same hash value return that you'd expect. So only those with the appropriate secret key should know how to reconstruct it, taking data, running it through the hashing algorithm with the secret key to get the exact same hash value, thus verifying if the message is actually identical. So, for example, paid Terry Smith $100. With that being the data, and we have a secret key, we can actually hash it, and we would have a hashed value. Well, that would be called the HMAC because we use the secret key. What we would then do is send it. The receiver would then decode it, look at the message, and then verify it. Use what they decoded and their secret key, and they would hash it the exact same way to compare the two hash values. If they are the same, then we know that the file was unmolested in transport. This is a way to verify the authenticity of the message. Alright, so let's put all of this together. So we verify the HMAC value, we get the received data, we have the secret key, we hash it. As long as we get the same value, then we know the generated HMAC is verified. The integrity and authenticity has been verified. If they're not the same, then we discard them and we move forward. So how does this work for like a Cisco router, for example? So between the two devices, we actually have the same ability to look at the links, look at the networks, look at the addresses, the types of links, the costs, and we have the ability to do that. And that would be an example of a router HMAC. And that will be done using like OSPF and the router authentication mechanism. If the matching hash value is not matched on the other side, the matching router, R2 in this example, would not allow for the connection between the two. We do have a lab hashing things out, and that's creating hash values using OpenSSL and verifying hashes. Alright, the next main section is about confidentiality. So data confidentiality typically comes in two main flavors, and these are the encryption types: symmetric and asymmetric. So the difference is how they use the keys. Symmetric, one key to encrypt and one key to decrypt. Sorry. The one key to encrypt is the same as the decryption key. Asymmetric is one encrypt, one decrypt. Different keys for encryption, different keys for decrypting. When we're looking at a symmetric, we're looking at things like DES or triple DES or AES. And again, they have a pre-shared key that is used to encrypt and decrypt the data. Same key. It is faster, and it's common with bulk encryption and like VPN type traffic. With asymmetric encryption, again, separate keys for encrypting from decrypting. It is a little slower, and you commonly see this with like HTTPS or accessing secured sites. They use things like the RSA algorithm, and they use the PKI system, or the public key infrastructure. Public key infrastructure allows for the management of these separate keys. So again, looking at this figure, symmetric versus asymmetric. Symmetric, same key to encrypt and decrypt. Asymmetric, one key to encrypt, different key to decrypt. Alright, so let's dive a little deeper. Let's look at symmetric keys a little bit more in depth. Again, pre-shared key, they have the same key for encrypting and decrypting. Most key encryption keys are about between 112 and 256 bits. The longer the key, the more secure. Symmetric encryption algorithms are sometimes classified as a block or stream cipher. They can do it in blocks or in streams. Here is an example of a block cipher. A block cipher will take blocks of chunks of data, maybe 64 bits. If we're using DES, it is 64 bits. If it's AES, it's 128-bit blocks. And then it goes to the algorithm, and it will then encrypt the message. A streaming cipher, basically it's 1 bit at a time instead. Streaming ciphers will encrypt the plain text 1 byte or 1 bit at a time. The ciphers are basically a block cipher with a block size of either 1 bit or 1 byte. Stream ciphers are typically faster than block ciphers because it's continuously being encrypted. Examples of stream ciphers could be like an RC4 or A5, which that's what a lot of the GSM cell phone communications are used for encryption. Alright, so other forms of symmetric key encryption, again, AES is going to be the most common. We have a SIL or RC or DES or triple DES. Realistically, AES is the one that you need to pay the most attention to. That is the current and strongest version of symmetric key encryption that is currently being used. It offers combinations of 128-bit, 192-bit, and 256 key length, and they encrypt 128, 192, and 256-bit long data blocks. Alright, so now that we talked about symmetric, let's talk about asymmetric. Again, asymmetric is also called the public key algorithm. They're based on different encryption and decryption based keys. Asymmetric, we use a public key and a private key. Both keys are capable of the encryption process, but they complementally pair with one another for decryption. The process is reversible, so data that is encrypted with a public key will require the private key to decrypt it. So, let me grab my pen. We have our plain text. We use our encryption key, public key will be encrypted, and to decrypt it, we will need the private key. Asymmetric algorithms achieve confidentiality and authenticity by using this process. Normally, the key lengths are between 512 and 4096. The asymmetric algorithms are substantially slower than symmetric, but they do offer a much larger bit size and different keys. So common ones for asymmetric are going to be things like DH, or a digital signature standard, or the elliptical curve. DH is going to be a big one for VPN technologies. This algorithm will allow the two parties to agree on a key, and they will be part of a key exchange. So how does this work? So basically the public key will encrypt it, the private key will decrypt it. That provides the confidentiality. Public key encrypts the message. Private key decrypts the message. So when there is a public key in use to encrypt the data, the private key must be used to decrypt the data. Public key encrypt, private key decrypt. So this process can be summarized using the formula: private key encryption, public key decrypt. This allows for authentication. You'll notice, I'm going to go back one slide. Public key encrypt, private key decrypt. Confidentiality. Authentication. Private key encrypt, public key decrypt. Authentication. They are switched. When we're talking confidentiality, public key is the encryption, private key is the decryption for confidentiality. For authentication, private key encrypt, public key decrypt. They are different. So I want to point that out. When the private key is used to encrypt the data, the corresponding key to that private key, the public key, must be used to decrypt the data. Because only one host has the private key, only the host could have encrypted the message, providing authentication for the sender. So let's go through an example. Here we have Alice sending a message to Bob. Alice will use her private key to encrypt the message. Bob will get the encrypted message and will use Alice's public key to decrypt the message. Alice's public key will decrypt the message, thus allowing us to read the message. So if we want to combine, we can do that. If we have a plain text, we can use Bob's public key. If we have a hash, we could use Alice's private key. We send that over, we get the encrypted hash from Bob's public key, plus Alice's public key, we get a hash. Then we could use Bob's private key to decrypt it. So combining the two asymmetric encryption processes provide message confidentiality and authentication and integrity. This is a lot more complicated than they needed to make it, but essentially we can hash the messages and then we could use the keys to encrypt the hash. The DH, the Diffie-Hellman, is an asymmetric algorithm that allows two computers to generate an identical shared secret without having communicated before. The new shared key is never actually exchanged, just calculated individually. The key can be used by an encryption algorithm to encrypt traffic between the two systems. Following are two examples. So the data exchanged using an IPsec VPN or SSH data is exchanged. Basically, the DH is calculated and verifying the keys so that we could then actually get a shared secret message or shared key, secret key without ever actually having been in communication with one another before. DH groups are group 1, 2, 5, 14, 15, 16, and they are all going to be based off of the different bits. Group 1 is 768 bits, group 2 is 1024 bits, group 14 is 2048 bits. Realistically, most people use groups 2 or 14, but it's when you're doing the VPN, you're going to look at what is actually functional. The DH key agreement can also be on the elliptical curve in cryptography, and those are DH groups 19, 20, 24, and they're also supported by Cisco iOS, but they are outside the scope of this. Realistically, understanding the DH group is looking at asymmetric keys and understanding the bit length. We do have a video in our chat or in our course shell, explaining kind of cryptography at a very low level. We have a lab for encrypting and decrypting. We have a lab for setting up our scenario and actually encrypting a file, as well as encrypting and recovering an encrypted password. We have a lab examining Telnet and SSH. So we have a lot of labs in this chapter. Moving on to our next section is our public key cryptography. So we know that this is asymmetric, and we know that public key is dealing with key exchanges. So the first use of the public key cryptography is going to be digital signatures. These are mathematical techniques used to provide authenticity, integrity, and non-repudiation. You notice digital signatures. Typically on like HTTPS type websites, they use a digital certificate to trust the different websites. So again, digital signatures are symmetric. The digital signatures are commonly used in two situations: digital certificates and code signing. That way we can provide some type of integrity of files after they've been verified. The digital signature standard, or DSS algorithm, is used for generating and verifying digital signatures, and they are things like the DSA, RSA, and the ECDSA. Realistically, the digital signature algorithm and the RSA are the two big types of certificate standards or algorithms that we should be looking at. The RSA is an encryption standard used for algorithm that is becoming more difficult to break when we look at an asymmetric encryption. Digital signatures are commonly used to provide some level of assurance, authenticity, and integrity. Again, looking at either the code or looking at a web content. When they're signed with a certificate, we trust the third party, or we trust the website because we trust the signer of the certificate. You go to your bank. How do you know that it's the bank website? The bank has a certificate that was issued by like VeriSign. Well, we trust the bank because we trust VeriSign. That's how that digital certificate trust hierarchy works. When we install an application, the publishers of the software have a digital certificate for the software. We install the software because, again, we trust the publisher. Basically, this provides a certain level of non-repudiation that that code, if it has a signature, was verified. So digital signatures, code signing, if we're looking at a certificate, we normally see a issue to, could be a company or could be a website, issued by, who's actually issuing it. It will be done through a certificate authority, or CA, and it will give a valid date range. If we look at the details, we can see the details of it. Normally, we would look at the certificate path. That's where our computer or our device is saving the certificate. We have certificate information. We have digital signature details, and we have the digital signature itself. Basically, we look at the details, and we can see the details of the certificate. At our level, the big one is issued to, issued by, and the valid date range. When we look at the details, we can look at a much more in-depth view of the certificate, like the encryption type and things like that, but oftentimes that is way outside the scope of what the average person is going to be looking at. The digital signature for a digital certificate will look at things like issued to, issued by, and expiration date. If we look at a physical certificate, it's the same thing. We look at who issued it, who they issued it to, and what the expiration date is. That way we can have an independent verify that that is actually legitimate, whether it's a physical certificate or a digital certificate. Okay, so now let's try to look at this in a more realistic or real-world scenario. So we're going to look through a scenario where we are using the digital signature. So Bob orders something. They have a confirmed order, and with that they're going to purchase something off of a website. So Bob will confirm the order and his computer will create a hash of the confirmation. The computer will encrypt the hash with Bob's private key. The encrypted hash, which is the digital signature, will be added to the document, and then the order confirmation is then sent to Alice over the internet. They can compare the two, as well as the order form and the signature. As long as they are equal, then we know we are good. To further this through, what we are going to do on the receiving side. So when Alice receives the digital certificate signature, the process will kind of go in reverse. Alice will receive and accept the order from Bob's computer, looking at Bob's digital signature and Bob's public key. Alice's computer will then decrypt the signature using Bob's public key, which reveals the assumed hash value of the sending device. They will verify the hash are the same. If they are the same, then they will move forward. If the hashes match, the document must be authentic. That means the confirmation was sent by Bob and has not changed. Thus, the order is complete. Alright, the next section is about the authorities and the overall PKI trust system. Because oftentimes we don't think about how we verify our trust documents. So we have a public key management. So when we establish an asynchronous connection between two machines, they will exchange key information. A trusted third party on the internet will validate the authenticity of the public keys using digital certificates. These third parties issue credentials that are very difficult to forge. Not impossible, but difficult to forge. From that point forward, all the individuals will trust the third party, simply accept the credentials that the third party has issued. The overall PKI infrastructure consists of very specific specifications, systems, and tools. And all of these are used in creating, managing, and distributing, using, storing, and revoking digital certificates. The big thing here is we have a centralized authority called a certificate authority. These certificate authorities, CAs, are used to create the digital certificates by typing a public key information or a public key to confirm identity, such as a website or other individual. This allows us to confirm the identity of something, because we trust the third party, and who they trust, we inherently will trust. So, the PKI infrastructure in a nutshell. We have a support system or some type of framework that will facilitate that trust. We have the certificate containing the entity or the individual's public key, and that is issued by the certificate authority that validates and issues the certificate. The certificate store will reside on a local computer, and the local computer will verify it. The certificate authority is a trusted third party that manages the keys. The certificate database will actually be checked periodically to verify the certificate key is 1, valid, and 2, hasn't been revoked. So this is the general framework used to describe the public key infrastructure. Looking at it in a different way, we have a certificate authority. They are the ones that are issuing the certificates. So they will issue us a certificate. We may look at the certificate and we may verify the certificate. And when we go to verify, they will verify it through the certificate database to verify that they are legitimate. The certificate authority, so that it is not bogged down, they will actually use a registration authority as a subordinate certificate authority. So the registration authorities, the RAs, will act on behalf of a certificate authority. We could also have subordinate certificate authorities that act on behalf of a root or top level certificate authority, issuing certificates on their behalf. So let's look at the certificate or the PKI authority systems. So we know that the top level is certificate authority, the CA. Many vendors do provide CA services as well as other managed services to end users. Organizations may also implement private systems. CAs issue certificates based on classes, and the classes are going to be based off of a description. So, Class 0 is used for testing in situations no checks have been performed. Class 1 is used by individuals who require verification of an email. Class 2 is used by organizations for proof of identity is required. Class 3 is used for servers and software signing. Class 4 is used for online business transactions between companies. And then Class 5 are used for private organizations or government security. So these are the 6 main classes. The class number is determined by how rigorous the procedure is. How much do we want to verify? Not all certificates are created equal. If you want to have a trusted site that is the highest level security, you may go for a Class 5. If you are a business selling something online, you'd go for a Class 4. If you are a personal website not really doing anything, you may go for a Class 1, maybe a Class 2. The higher the class, the more money you're paying. The higher the class, the more trusted the certificate is. So we have a few different types of topologies for these systems. We have a single root PKI topology, and that is where everyone goes to the root certificate authority to get certificates. We have a cross-certified certificate authority, and that is where we have a root certificate authority, and they actually then issue certificates through their subordinates. That way the certificate authorities, the main CAs, are not bogged down, but the fun part with that is the main certificate authorities can still issue certificates directly to individuals if they want. This is more of a peer-to-peer model, and this is kind of makes it a little bit less centralized. We have a hierarchy certificate authority, and that is where the root CA does not issue certificates to subordinates. They only issue them to subordinate certificate authorities. Those certificate authorities then issue them to computers or servers or other things. Here, the root CA, the highest level CA, issues certificates only to subordinate certificate authorities. While they can also still issue them to end users, they're typically not done in that manner. The interoperability of the different PKI vendors, the different vendors don't really matter. It's more of a which one is the most trusted. That's the thing, is they're all fairly well trusted. So the main interoperability between a PKI and its supporting services is the concern, because the different vendors have proposed different implement priority solutions. To address this, the Internet Task Force has published the Internet X509 Public Key Infrastructure Certificate Policy, and that is actually RFC 2527, and this outlines how all the different certificate authorities are supposed to behave. So when I said all certificate authorities kind of do the same thing, that's because they all should be following the X509 version standard. Currently, the X509 version 3 standard defines the format of the certificates. LDAP and the X500 are the protocols that are used to query the directory services, like Active Directory, for verifying usernames and passwords. That is different than a digital certificate, that is 509. A X500, again, is more like LDAP with Active Directory. So certificates should have an enrollment, authentication, and some type of revocation or revoking process. These certificate authorities typically will have a certificate key that verifies the certificate that are issued by the CA, and this is vital for the proper operations for the PKI system. The certificate enrollment process is used by the host to enroll in the PKI. To do so, the certificate will actually retrieve in-band over a network, and the authentication is done out-of-band using a telephone, for example, or some other out-of-band mechanism. The system will enroll the PKI contact, the CA, to request and obtain the digital certificate. This in itself will be self-signed by the certificate authority. Basically, the final stage will verify the the CA certificate that was self-signed, that was authentic, and will then perform an out-of-band method for obtaining the fingerprint of the valid certificate authority identity. Basically, they want to verify the certificate authority and make sure that it was actually the one that was self-signed, making sure it was signed by the appropriate certificate authority, even if it is self-signed. Only the root certificate authority can self-sign. Everything else below it must verify against the root certificate. This is actually a lovely in-depth process that we needed to go deeper into, and typically within the Cisco realm, you just have to understand the hierarchy and the purpose of the certificates, not so much the in-depth process, because this actually is not even deep enough for the actual enrollment, authentication, and revocation of it. In one of my server lectures, I've actually discussed certificate authorities and PKI way more in depth. Anywho, so after we get done with that, we do have a certificate lab, and we actually look through the certificate lab so that we understand the certificate authority, and checking for man in the middle. Alright, so moving on, the last main section is about the application and impact of cryptography. So PKI is used by many different things to perform some basic security. SSL or TLS for certificate-based peer authentication, or HTTPS web-based traffic, or VPN traffic, or sending secure email, or sending secure messaging, or encrypted file systems, or code signing, or smart cards, or storage devices, or. Lots of stuff use PKI in performing and protecting and encrypting their information and data. So an encrypted network transaction, for example, will actually need a valid certificate. If we're doing VPN, the VPN itself will use a certificate often, and they're going to be looking at the date range, the certificate error, if the certificate has any errors, if the certificate has been revoked or anything like that. When we go to a website, we're looking at HTTP over SSL or via SSL. TLS or SSL in this regard are going to be the exact same thing. TLS is the newer versions of SSL and are taking over the older versions of SSL. Oftentimes, when we are actually verifying a website content and encrypting the data over a network, we are actually doing that with the certificate that is issued. So the security analyst must know how to circumvent and solve these types of issues. So here's a few different types. Configure rules to distinguish between SSL and non-SSL based traffic, HTTPS versus non-HTTPS traffic, enhance security through server certificate validation using the appropriate CRLs, certificate revoke lists, implement anti-malware for protection of URL filtering and HTTPS-based content, and deploy things like appropriate IDSs and IPSs so that they can actually prevent intrusions based off of invalid HTTPS-based traffic. Cryptography is also very dynamic. It's always changing, it's always growing, it's always being modified. An algorithm today may be insecure tomorrow, so it really just depends on what we are going through. There are two main ways in which cryptography impacts security investigations. First, attackers can direct can be directed at specifically targeting the encryption algorithms themselves, or the security investigator could also affect the data or the originality of the data because it's hidden in plain sight by encrypting the data. If the data is encrypted, it's hard for the investigator to actually review because it's encrypted. So it really just depends on the purpose that you're trying to get. Sometimes people encrypt data just because they want to encrypt the data. It doesn't mean anything malicious, it just could be you want to secure your stuff. Data encryption is becoming secondhand in almost any type of modern day device. Your mobile phone has encryption. Windows 10, Windows 11 has built-in encryption. Macs, Linux machines all have built-in encryption. So encryption is becoming pretty standard place now. Alright, so we are wrapping up our cryptography summary. We looked at a ton of things. We looked at the elements of cryptography, integrity, authentication, confidentiality, non-repudiation. We looked at hashing and hashing messages. We looked at different types of encryption, asymmetric versus symmetric. We looked at different protocols, DES, triple DES, AES versus RSA, and the PKI model. We looked at public key encryption, private key decryption for confidentiality. We looked at private key for encryption, public key for decryption for authentication. We looked at the overall components of a PKI system. That would be the specifications, the systems, the tools, the way that they manage, distribute, use, store, revoke all the digital certificates, the components of a PKI system, and we looked at many of the common features of the PKI system. And that is all for this chapter.
If you have any questions or anything, please feel free to reach out. Again, with this material, being able to ask questions and discuss some of the topics in the lecture help build long-term retention, so do not be afraid to communicate with this topic. Again, I'm here if you need anything. Thank you.